In this section, we will look at the physical and chemical properties of matter and how to determine if you're seeing a physical or chemical change, and then we will look at elements and how they combine to form compounds. So your physical and chemical properties are two different descriptions that you can apply to the chemicals around you. A physical property is something that can be observed without changing what you're working with. So for example, if I take a bar of gold, I can describe its density, I can describe its mass, I can describe when it would melt, I can describe how much I'd have to heat it to make it turn into a gas, which would be very, very high. And I can describe what it smells like. That may not have much of a smell. If I take that gold bar and I melt it, I'll get a liquid, a shimmery liquid. It will have different characteristics, a different density perhaps. It will have a different appearance. But that's just a change in state. It's still gold. If I take that gold bar and pour it into a mold for a gold bar, I take the liquid and pour it into that mold and let it cool, I'll get out the gold bar again. And so those are all physical properties. As long as we're still working with gold, it's physical properties. Your chemical properties are going to be things that have to do with a chemical reaction where you start with one substance and it changes to a different substance. So for example, if I had wood and I took that wood and I heated it up under the right conditions, it would burn. And when it burns, you get out the ash, which is charcoal, and you get some carbon dioxide that goes off into the air, and you get water. Those products are very different from the wood, and I could change several of the conditions that happen to reverse them, and I wouldn't get my wood log back. So that is a chemical change. So here are some definitions that will be useful when we're talking about our physical and chemical properties. A chemical bond holds two atoms together. It's the attraction between those atoms. And it will either be created or removed when there's a chemical change that goes on. A chemical change is a rearrangement of the atoms and how they're bonded. So, for example, water has one oxygen in the center with two hydrogens on the outside. And so we call it H2O, two hydrogens with one oxygen. If we do electrolysis, which is something we'll talk about in another chapter, but you apply electricity under certain conditions of ion concentration, and it breaks those bonds, and you get out hydrogen gas and oxygen gas. So we have caused a chemical change. You end up with two hydrogen atoms bonded together and two oxygen atoms bonded together, which we would write as H2 or O2. And we've changed the identity of what we have by doing that electrolysis. A chemical reaction is the overall process that leads to a chemical change. And we will be studying chemical reactions in an upcoming chapter. But what it does is you show what you started out with, they draw an arrow, and then they show what you end up with in your chemical change. So how do we determine the difference between a physical change? Notice the gold melted, it looked different. How do we know it's still gold? And a chemical change where you have a reaction take place, but perhaps it looks very similar when you're done. The physical change will involve changes in temperature, pressure, or volume. So, for example, if I took the gold bar and I melted it, I had to apply heat. If I reverse that and cool down the gold bar, will I get back solid gold? And the answer is yeah, I do. And so if you reverse those changes back to what they were, then you get the original substance back out. So if I take water at 25 degrees Celsius and freeze it, bring it below zero, I'll get solid ice, and it will expand in volume. You've probably learned this if you've ever put something in the freezer in a container that didn't expand. You tried freezing it and the glass broke or whatever the circumstances you were in. It looks very different. It's not wet anymore, all that kind of thing. But if you take it out and warm it back to 25 degrees, you get water again. So that's another example of a physical change. If you have a chemical change, what happens when you reverse things? You don't get back what you started out with. So if I took my wood and I cooled it down and stuck it back in that fireplace, it's not going to reform into a log. It's just not going to reverse like that. So atoms are your smallest unit of each type of element. The elements don't always exist when they're by themselves as a single atom in nature. A lot of them do, or a lot of them exist as an infinite clump of that type of atom. So like if you were to take sodium metal and refine it, you'd get out a lattice of sodium atoms. But a lot of the non-metals exist as diatomic, which means two atoms when they're by themselves. So hydrogen comes as twos, nitrogen, oxygen, fluorine, chlorine, and bromine. These all come as twos. So they're called diatomic, and when you see them in a chemical reaction, if they're by themselves and not in a compound with other elements, they will be shown as two. Sulfur comes as 8. So if you have just sulfur by itself, it'll say S8. Your compounds are atoms of different types joined together. So for example, carbon dioxide, which is in the air you breathe out, it's one of the waste products of what our body processes, is made of 1 carbon and 2 oxygens. Now you'll notice they have a 2 written by the oxygen, but they don't have any number written by the carbon. When there's no subscripted number by an element, it means you have one of those in each molecule. These compounds have their own physical and chemical properties. They're independent from the physical and chemical properties of the elements that make them up. So, for example, you probably have sodium chloride in your pantry. It's table salt. Sodium metal is soft. It's kind of like butter, but it's shiny and it's silvery. And if you were to take it and cut it, it would cut like butter. Really a soft metal. If you were to put it in water or expose it to water, it reacts so violently it lights on fire. So that doesn't sound like the safest element, right? And they actually pack it in an oil so that it doesn't get exposed to water. If you have chlorine, Cl2, as just a gas by itself, it is really nasty. They used it in World War I as a way of fighting, and as the chlorine gas came towards you, if you breathed it in, you died. So if you sent it towards your enemies to kill everyone in the trenches and the wind shifted, it would come back the other way and kill all your people in the trenches. Nasty stuff. But you combine sodium and chlorine together in a 1-to-1 ratio and you get table salt, something that you need in your body to a certain degree. So notice totally different properties. Another example would be benzene. Benzene is made out of 6 carbons and 6 hydrogens combined in a ring. And carbon is black and brittle and it's a solid. And hydrogen is a clear, flammable diatomic gas. If you take hydrogen and put flames near it, it lights on fire really strongly. It makes a noise. It happens so fast. But as benzene, it is a clear carcinogenic liquid with a very characteristic smell to it. And they use it in a lot of organic chemistry labs. They develop a lot of drugs and things like that with benzene as a solvent because it is easy to remove the benzene from what you're doing.